Hey guys, so you should have just finished your video on L'Hopital's rule. First period, you would have watched that on Monday, so today should be Tuesday for you guys. Seventh period, ambitious, but we're doing 2 videos in one day, so let's get started. Your fall semester review is counting as a test grade for this quarter, so that is going to make this assignment a little bit more important because first of all, it's a test grade, but second of all, this is your best tool for preparing for your semester exam, which is also going to be a pretty big grade, right? So let's get started. Questions 1 through 9, you have limits as x approaches specific values. So remember, the first thing you should try for that is substitution. Okay, so an example of substitution I'm going to show you is number 5. So if we want the limit as x approaches pi thirds for tan x, we're just going to plug that in. So we would have basically the tan of pi thirds, which I can then break down into sine divided by cosine of pi thirds. Okay, then if you love unit circle, that's fine. I'm going to do hand trig. So 0, pi 6, pi 4, pi thirds is here. Fold it down. Okay, then sine, I see that I have root 3 over 2 fingers. Divided by, and then for cosine, I just have 1 finger above, so that's a half. And then remember, when you're dividing fractions, you just do the top one multiplied by the bottom one flipped. So I would have root 3 over 2 multiplied by 2 over 1. 2's cross out, answer would be root 3. Okay, so if you can plug it in and get an answer, that's awesome. Okay, now let's jump up to, let's take a look at number 2. Okay, when I take a look at number 2, I see x is approaching -1. So I would have -1 squared plus 3 times -1 plus 2 over -1 squared minus 1. Well, okay, -1 squared is +1, and 1 minus 1 is going to give me a divide by 0. Okay, however, I think my video is a little laggy. However, very important here that if the top comes out to 0 as well, that means L'Hopital's rule could potentially fix this limit. So let's see if it does. -1 squared is a +1. That's going to give me a -3 and then a +2, which means that if you get 0 over 0, remember, that means you have to do more. Okay, and so my options would be factor cancel or L'Hopital's rule. So I'm gonna go with L'Hopital's rule just because we just did it yesterday and it's a good little reminder. So I'm gonna have to write smaller here, but my limit, I'm gonna retry it with x approaching -1, but I'm gonna take the derivative of the top and the bottom. So on top, x squared plus 3x plus 2, my derivative is 2x plus 3. On bottom, my derivative is just a 2x. And then I'm going to take that x approaching -1. I'm just going to try to plug it in again. Okay, so on top, I have 2 times -1, which is -2 plus 3, which is 1 left over. And then on bottom, I have 2 times -1, which would be a -2. So my answer would be -1/2. Okay. So if I plug it in and get an answer, great. If I plug it in 0 over 0, that means I got to do more. Okay, let's now take a look at number 4. What if I'm doing x approaching pi halves of tan x? Okay, well, for tan x, remember, we're just plugging in our pi halves here. We'd have the tan of pi halves, which would be sine pi halves over cosine pi halves. Then I'm going to do my hand trig. Pi halves is your thumb. All my fingers are below my thumb. That means this sine is 1 because that's the biggest that it can be. But then if I'm on my thumb, there are no fingers above my thumb. That means I get a 0 on the bottom. Remember, 1 over 0 is not fixable. L'Hopital's rule can't fix it. That limits a DNE. Okay, and then remember what we said. No, you don't have a limit if it's a number over 0. Not allowed. Okay, so let's take a look at let's do number 8. Okay, so number 8, x is approaching 2. So I'm going to take my 2 here and just try to plug it in. So I have e to the 2 times 2 is 4, minus e to the 4. Then I plug in my 2 on bottom. E to the 4 minus 4, oh, that gives me 0. 2 minus 2, that gives me 0. That means do more. Now, this isn't the AP test, but we want to set good habits. Okay, so I'm going to scribble that out, okay, so that it shows. I know that's not a thing. I know nothing can equal 0 over 0. Okay, so I'm going to now try the limit again by taking the derivative. This is L'Hopital's rule. So I'm going to do the limit as x approaches 2. But my top function, e to the 2x, the derivative of that is going to need chain rule because it's e with a 2x plugged inside it. So that's going to be e to the 2x again, and then multiplied by 2. Now, e to the 4 is a constant. So when you take the derivative of a constant, that's just going to be a 0. Okay, so you can put the minus 0 if you want to. Then on the bottom, I have an x minus 2. Derivative of that is a 1. I don't know why I wrote that so misaligned, but this is the limit that we're doing. Then I'm taking my x approaching 2, and I'm going to plug it in right here. And then notice that fixes the problem. Well, then my limit actually does exist. Even though originally I got 0 over 0, this is fixable. So I plug my 2 in right there, and I'm going to have 2 e to the 4. Technically, it is over 1, but we know that the over 1 doesn't really change anything. Okay. All right, let's move to the next row. 10 through 12 are all definitions of a derivative. So let me remind you of what the definition of a derivative is. The definition of a derivative says, I can probably squeeze it in here, that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And so there was one day in class where I made us like work these out, and it kind of took forever. Okay, but then literally, I think it was the next day, we learned the derivative rules. So when you see a limit that follows this sort of structure, all that you need to do is 2 things. Find out what f is, and then take the derivative using the rules. Okay, remember, you would not ever work these out the long way on the AP test. Okay, so here's what that's going to look like. Let's say I'm doing number 10. Okay, f of x is this term behind the minus sign. That means that my f of x is tan x. But I know this is the definition of the derivative of tan x. And by rules, I know the derivative of that is secant squared x. And then that would be your answer. Okay, let's look at number 11. Okay, f of x is behind the minus sign. That means that it's the x cubed. And then I just take the derivative of x cubed using the power rule. That would just be 3x squared. Okay. Now, sometimes people ask this question, what about the minus sign? Okay, the minus sign is part of the formula. Okay, the minus sign is part of the definition. So that minus is not part of the f of x. That's not a negative x cubed. That's a minus in the formula, and then my function is only the x cubed. So you are going to ignore that minus sign, okay? All right, so your next section are limits to infinity. Remember, for limits to infinity, you are checking the end behavior of the graph. And remember, the rules that you use for those are Bobo, Botten, and Bedsey. Okay, remember that what we are comparing on Bobo, Botten, and Bedsey is where the bigger functions are. So the order, I'm going to put it here at the bottom, is that constants are the smallest, along with sine and cosine, then logs, then power, and then exponentials. Okay, that's the order. And then if you don't remember the difference between a power and an exponential, a power is like an x squared, an exponential is like a 2 to the x. Okay, so if the x is the base, that's a power. If it's the exponent, it's an exponential. They also remembered that log does include any natural logs. Those are the same category. Okay. So I don't want to do a ton of these just because they're pretty easy. Let's say we wanted to do number 15, okay, just for fun from the top row. I'm looking for the biggest power on top. I see that I have an x squared. Biggest power on bottom, I have an x cubed. Then I would say, where is it bigger? Bigger on top or on bottom? Well, x cubed is bigger. That means that's a BOBO and that limit goes to 0. Okay, also notice this little blurb that I wrote here. Recall that for polynomial ratios, meaning that these are just like x squared, x cubed, stuff like that. Bobo and Betsy are the same. It doesn't matter if x is going to infinity or to negative infinity. So like the negative infinity here makes no difference. This was positive infinity, I'd still put 0. Okay. All right, go down to the next row, 16, 17, and 18. X is still going to infinity. Okay, so I'm going to look at, let's say this first one here. I have an x5 over an x2. Okay, well, if I'm comparing those two things, obviously x5 is going to be bigger, which means that that's a botan, which means that that limit is a DNE. Okay. Same thing with, let's say we're doing number 18, whatever, okay? Or actually, let's not do 18, let's do 17. 17, you'll notice, okay, 6x5, 15x2. Okay, that one's also a DNE because it's bigger on top. It's the exact same equation, in fact. Okay, but there is one detail that's different on these. So let's read the little blurb right here. Recall that for polynomial ratios, botan can be described with the infinity that the end behavior approaches. So what that means is that I could say, well, this limit doesn't exist, right? But I could also be more specific and say whether it's approaching infinity or negative infinity. Okay, and so basically all that you would have to do for that is take the sign of your infinity and then plug it into the powers and see how it works out. So for example, if I was doing number 16, x is approaching infinity, well then I would have 6 times infinity to the 5th divided by 15 times infinity squared. Well, if infinity was already positive, the top is going to stay positive. Same with the bottom, I'm squaring it, that's going to be positive. So overall, I could say this is DNE, or I could say that it's approaching positive infinity. Okay, and both of those are right. That just means that that end of the graph, not only does it not have an asymptote, but it's going up forever and ever and ever. Okay, now let's do 17. So 17, it's the exact same equation, but now I'm approaching negative infinity. So if I put, move my mouse here, if I put a negative infinity in the top, well, that matters because if I put a negative to a 5th power, that's going to stay negative. Now on the bottom, if I plug a negative in, it doesn't matter because when I square it, that negative is going to cancel out. But if I divide a negative on top with a positive on the bottom, that means that that end is going towards negative infinity. Okay, so specifically what that means, you don't have to write this, but you can if you want to, is that as x approaches infinity, f of x is approaching infinity as well. But that as x approaches negative infinity, f of x is approaching negative infinity. That means that end is going down versus this end is going up. Now, Those don't always have to be the same sign. So for example, take a look at number 18. I have an x6 and an x2. So again, this is another bottom because I have more x's on the top than I have on the bottom. So I know that it's a DNE. But if I wanted to be more specific and say which direction it was not having a horizontal asymptote to, then I would take that negative infinity and I would plug it in 6 negative infinity to the 6 over 15 negative infinity squared. And what you're going to notice is that because both of those have even powers, I end up basically kind of just like losing my negative. So negative infinity to an even power turns out positive. That negative infinity squared turns out positive. And if you divide two positives, what do you get? A positive infinity. So for this equation, you would say as x goes towards negative infinity, which would be like the left end of the graph, my f of x would be approaching positive infinity. Okay? So remember, those are describing the end behavior of a graph. Okay. All right, so if you will, please, let's turn the page. We have some more limits to infinity that I'd like to look at. But remember, overall, we're doing Bobo-Botten-Bedsey. Okay, if x is going to infinity or negative infinity, doesn't matter, still Bobo-Botten-Bedsey. Okay, also, please feel free, Dr. Betts, the sub, please feel free to pause the video if people need a second to write stuff down. That's no problem. Also, if you guys need to go back and watch these videos, they're all on the website. So just like Dr. Betts is playing the videos here, you can access them from home in case you'd like to watch one of these videos again, okay? So 19 through 22, you'll notice that we have some exponential terms. Remember that if x is approaching negative infinity on an exponential term, that is going to turn into a fraction. So here's what I mean by that. Number 19, I see x is going to infinity. It's a Bobo-Botten-Bedsey. I have a 2 to the x and a 5 to the x. And then also, let me just remind you, I know we haven't looked at this in so long, Bedsey only applies to polynomials. You can never have a tie with exponentials. So I've had kids say, like for this one, oh, it's a Bedsey, 2/5. Okay, 2 to the x and 5 to the x are both exponentials, but if one of them is bigger than the other, you have to pick. So I would be like, okay, well, 2 to the x and 5 to the x, which of those is bigger? 5, which means that this would be a bigger on bottom, which would make that 0. Okay, so you can only apply Bedsey if the top and the bottom are both polynomials. If that's not the case, Bedsey's out. You can only pick Bobo or Botten. Okay. Now take a look though at number 20 for me, please. Number 20, x is going to negative infinity, and I notice that I have multiple exponential terms. So if x is going to minus infinity, that's going to take my 2 over x, or 2 to the x, and make it a 1 over 2 to the x. And my 5 to the x is going to be a 1 over 5 to the x minus 4. And then from there, if x is going to infinity and I'm doing Bobo-Botten-Bedsey, well, then now all of a sudden these exponentials that used to be really big, now 1 over 2 to the x is really small. Not only is it small, but it's basically a Bobo and goes to 0. And so I know that's kind of one of the weird things about exponentials, right? Is that when you're going to infinity, they're the biggest. But when you're going to negative infinity, they turn into fractions. And then 1 over 2 to the x is going to go to 0. Okay, same on the bottom with the 1 over 5x. So basically I have 0 minus 16 over 0 minus 4. Well, then that's negative 16 divided by negative 4, which is going to end up being positive 4. Okay, so you have to watch out for exponentials. If you're going to infinity, everything's normal. But if you're going to a negative infinity, that's when it gets a little weird. Okay. Next one I want to look at is number 25. Okay, x is going to infinity here. And I see that I have a 6x versus a 2x. Okay, so overall, I'm looking for Bobobot and Betsy. I see that 6x and 2x, this is going to be a Betsy, because I have the same power. They're both linear x's, okay? But on top, I have a 6. On bottom, I have a 2. So that means that this is going to go to 3. Okay, so far so good. Absolute values also can get a little weird if you go to negative infinity. Here's why. When I take my negative infinity and I plug it into the absolute value bars, I'm going to have negative 6 because of the negative from here, right? But I'm going to put it in absolute value bars. So really, that top 6x is really a positive 6x. Oops, right here. Okay, versus on the bottom, when I put this negative in the 2x, that negative is going to rub off on the 2 and it's going to stay negative. So the other side will go to negative 3. Okay, so think about the difference. If it's absolute value or exponential, the two ends could potentially come out to be different. You just have to kind of check. Okay. All right. Let's take a look at number 29. So it says, use the graph of f of x to the right to answer the following questions. So when is f increasing? Okay, well, remember that f increasing just means that I need to have a positive slope. So I see here that I'm decreasing, then I'm increasing. This little blip here, that doesn't count as a positive slope. Okay, technically, yes, that one value is bigger, but then it goes right back down to the start. So you would not consider this little weird thing that happens here to be increasing. So increasing between 0 and 1, you could write it like this, or you could write it like this. Okay, whichever notation you like better, you should be comfortable with both because they'll both be on the AP test. Part B. For what values of x is f of x discontinuous, and then what types are they? So the types of discontinuities are removable, jump, and then infinite. Okay, those are the 3 types of discontinuities. A removable is basically a hole. A jump is when you have 2 limits that exist, but they just don't equal each other. And then an infinite is when you have a vertical asymptote. Okay. So I don't really know what to put for jump. I'll put something like this. Okay, where they just kind of like miss each other by a little bit. So if I'm looking at this graph, I see 2 discontinuities. First one obviously occurs at 1. Then I need to classify it. So I see I have a limit on the left, it's 2. I have a limit on the right, it's 1. But because they don't match, this would be considered a jump. So I'm going to say x equals 1. There's a jump discontinuity. Okay, and then also at 2, okay, that's called a removable discontinuity because it's a hole. Okay, then the last question says, where is f continuous but not differentiable? Okay, so let's review just briefly the difference here. Okay, in order for a graph to be continuous, it just has to be connected. Okay, a lot of pre-cal teachers will say, if you can draw it without picking up your pencil, it's connected, it's continuous. Okay, differentiable means that you can't have any corners, cusps, or any undefined slopes. Okay, that's what differentiable means. So I want my graph to be continuous. I want it to be connected, but I do not want it to be differentiable. Well, then that means that I need one of these features. So it has to be connected, but I have to have a corner, a cusp, or an undefined slope. Well, that happens at only one place, okay, right here at the origin. Okay, specifically at x equals 0. It is connected, which makes it continuous, but not differentiable because there is a cusp. Okay. All right, take a look at the next graph. I don't really want to do a ton of this one because I feel like these are so easy. But I'm just going to run across, I'm going to run across this line right here, the letter that starts with letter I. Okay, so it says I want x approaching 4 with a little minus. Remember, that means that I want the left side only. The left side limit only. So remember, what you do for these is you cover up the other side and you pretend it's not there. So if I want 4 from the left side only, I'm going to pretend like the graph never even existed on this side. I'm only going to observe the left behavior. And as I travel closer and closer to 4, I can see that I have a vertical asymptote. This is going down forever and ever and ever, which means that that is approaching negative infinity. Okay, you could also say it doesn't exist. That would be the same. Okay, now I want to do 4 from the right side, which means that I need to cover up the left side. So that means that this entire asymptote now is going to be gone. And when I look on the other side, I see that my graph comes closer and closer and closer to this dot, which when I remove my paper is right there. What is that? 1, 2, 3, 4. Okay. Now, this would still be considered, in case you care, okay, this is still an infinite discontinuity. Okay, it doesn't have to be, okay, it doesn't have to be an asymptote on both sides. It just has to be approaching infinity on one side to be classified that way. All right, take a look at K. K says, all right, well, as x approaches 4 for f of x, what's my limit? Well, if my left side is infinity, but my right side is 4, that means that this limit is a DNE. Why? Because the left and the right are not the same. Oh, sorry. Limit as x approaches 4 from the left is not equal to the limit as x approaches 4 from the right. Okay, so that's necessary for a two-sided limit to exist. Your left and right sides have to be the same. And so since that doesn't happen here, I know that I do not have a two-sided limit and it's a do not exist. Okay, let's take a look at letter L. I want f of 4. Remember, I am looking for a closed dot for f of 4. And so when I look at 4 here, I see there is a closed dot here. It looks like it's at a height of 4. So remember, limits, you're checking to see if they're headed to the same point. But f of 4 is a y value. All that you need is to know how high the y value is. You don't need to check the left and the right sides. Okay, then let's do maybe one more, maybe 2 more. Let's do letter N. If x is approaching infinity, that means that you are observing the right end behavior. You're looking over here to see what's happening at the far end of that graph. Well, we have to kind of extrapolate here, right? But it looks like it's flattening out, which tells me that that's probably 0. Okay. Then let's do last one in this set. Let's do letter P. I want the limit as x approaches infinity of f of 1 over x. Remember, the rule for compositions of functions for this is that you would take the limit and you would apply it to the middle. So I'm going to find the limit as x goes to infinity of 1 over x. And then once I find that result, I'm going to plug it back into function f. Remember that x approaching infinity is an end behavior question, which means that you're doing Bobo, Bot, and Betsy. So if I'm looking at 1 over x and I'm wondering who's bigger, well, 1 is a constant, x is a power. Even though it's a power of 1, it's still a power, right? So that means that that's a Bobo in there, which means that that goes to 0. Well, then I'm going to plug 0 back into f. And then if I look at 0 here, I observe my y value is a 4. Okay. All right, let's try to make it maybe like, see if we have a good stopping point coming up. Let's do 34 and 35. Yeah. Okay, 34 says, for x greater than 0, the horizontal line y equals 5 is an asymptote for the function. Which of the following must be true? Okay, so first let's start by just drawing a little picture here. So a horizontal line, y equals 5. 1, 2, 3, 4, 5. Okay, like this. Okay, then it tells me that I have an asymptote going towards this line. That means one of two things is possible. I could have an asymptote on, let's say, this side, or I could, you never know what happens in the middle. Crazy stuff in the middle. Okay, but on the other side, I could be asymptoting towards 5. But all that I know is that one of the sides is going to asymptote towards this horizontal line. Okay, we have no idea. Big question mark. What happens in here? I don't know. Okay, because asymptotes only tell me the end behavior of the graph. They don't tell you what happens in the middle. Okay, but then I look at this statement right here. It says this happens when x is greater than 0. That means that it has to be on this side. So if you look at your different answer choices, you should see, okay, this is my answer right here, that as my x's approach infinity, my f of x is going to approach 5. Okay, now if it was this side, x would be going to negative infinity, and then f of x would be approaching 5. Okay. Last one like that, number 35. This time I have a vertical line. Okay, so 1, 2, 3, 4, 5, vertical line right here. And then now it tells me that that vertical line is an asymptote. Okay, well then whatever I want can be happening over here on the end. I have no idea. Okay, but as I get closer to here, either I could asymptote up, I also could asymptote down, right? We don't know. Okay, we don't know what happens on the end. Maybe it's normal, but I know that here, my graph can't cross. Keep in mind, both ends could be going up or down. I'm just kind of drawing a version of it, okay? So does that mean that f of 5 is undefined? It could. However, what if this is a piecewise function? I have an asymptote here, I have an asymptote here, but then I'm like, f of 5 is 3, right? For a piecewise function, that's totally possible. So this is a good answer, but it's not the right answer because it says which one must be true. Most of the time at an asymptote, f of 5 is undefined. But there are graphs where you could have a defined point there, even though there's an asymptote. Okay, f of x not equal to 5, doesn't make any sense. Okay, look at letter C. As x approaches 5, yes, my f of x is going to plus or minus infinity. Yes. Okay. So the definition for a vertical asymptote is that x is going to approach your number and f of x is going to approach one of the infinities. Okay, versus a horizontal asymptote, your x is going to approach one of the infinities. And then your y value is going to be approaching a specific number. Okay. Actually, let me change this so it's not an A. I'm just going to put a number symbol there. Okay, so if your x is going to a number and your y's are going to infinity, that's a vertical asymptote. Versus if your x is going to infinity, that's a horizontal asymptote. Okay. All right, that's a great place to stop for today. So good job. Tomorrow we will be working through the second mini notes, and I'm just going to make one video and kind of squish it all together. So I will see you guys tomorrow. Bye.